thank you all for coming virtually and for giving me the opportunity to present this work. I'd like to thank Luke for inviting me to speak. As he indicated, this is work that was part of an effort to bring together different modeling centers and to get a sense of how and if the representation of certain modes of primarily atmospheric variability have improved in the latest generation of the CMIP6 models. As I'll indicate later, because of, we really wanted to get this work in before the working group first deadline, which was last December 31st. A lot of the results here are quite preliminary and may adjust as the CMIP6 archive increases. But we felt that this was a real attempt to coordinate analyses among the groups and to see if we could demonstrate any improvement in skill. So these are, again, this was a large effort, including Luke, myself, as well as lots of team members from NCAR, the Global Assimilation Office at NASA, as well as GFDL. And again, this was one of the main outcomes from a US Climate Modeling Summit last year. And the main funders were NASA, the Department of Energy, and NOAA, and they got together and supported this effort to do as comprehensive assessment and as we could within time constraints to see what is the current representation of key modes of atmospheric and oceanic variability among the models developed at these 6 US climate modeling centers. And so here we're really going to be focusing on modes like the El Niño Southern Oscillation, Mountain-Julian Oscillation, but we're also going to be looking at extratropical modes, which in the troposphere include things like the Pacific Decadal Oscillation, the North Atlantic Oscillation, the northern and the southern annular modes, and we're also going to be looking in the stratosphere a bit at processes controlling the representation of the quasi-biennial oscillation. So I'm going to try, in the event for people whose connections aren't that good, to specify what slide I'm on. So currently I'm on slide 3 in the PDF that likely was sent around. And again, this effort was very much oriented around producing something for the Working Group 1 deadline. And the team consisted of 12 members who all contributed to the analysis and writing of the manuscript. So specifically, we're going to be looking at these model versions shown right here in this table, which comes directly from the paper. And so what you can see is that primarily these are more climate models, but also we've incorporated some of the subseasonal S2S results from the Global Modeling Assimilation Office, as well as some of the GFS forecasts. So primarily we're focusing on an evaluation of climate modes, but there is some discussion of how this may potentially extend to short-term subseasonal forecasts. So practically over the course of several months last summer and fall, we met every 2 weeks, and I guess the unique components of this group were threefold. The first being that we had a range of people who have expertise in these different modes. Namely, John at NCAR led the analysis of ENSO. Peter coordinated and led much of the analysis of the extratropical modes. I focused on the quasi-biennial oscillation, and Angel led the analysis of the MJO. And so in addition to looking at these multiple modes, we were very aware that the measure one uses can very much skew one's perception of how the model is doing. So we made, when appropriate, attempts to really compare different analysis measures to assess the robustness of model fidelity. And then in what may be a more unique kind of aspect of this study, which was very much driven by the fact that we have access to intermediary model versions and model tags that aren't necessarily made publicly available. We made, when possible, substantial use of these intermediary model versions between CMIP5 and CMIP6. And this was our attempt to get a bit more of a lens into why certain changes in model development either enhanced or in some cases degraded model performance. So as Luke indicated, these results have been submitted in this paper right here, which is currently under review. We've submitted revisions and likely we'll hear back within the next few weeks or month. So this is the summary of the different models that we considered in our analysis. We have the NCAR, different versions of CSM1, CSM2, both low and high top, including WACM and CAM. We have E3SM, including, as we'll see in a later slide, an intermediary version of this with modified orographic gravity wave drag. We had submissions from GFDL, GIS, as well as some of the subseasonal forecast products that I described before. And so what we can see is just comparing the distribution of vertical layers, model top, horizontal resolution. There's quite a broad range of models represented here. I can just highlight, for example, we have models that have 102 layers and go all the way up to 0.002 hectopascals. And in that same token, we also have models that are have much lower tops and lower vertical resolution. So it's a pretty good representation of models in that sense. And then we also have a diversity of both convection and gravity wave drag schemes. So because our focus was primarily on evaluating climatic timescales, the bulk of our analysis was on submissions from these models as contributions to the CMIP6 historical deck. So the deck consisted of historical coupled atmosphere-ocean integrations, and this was not only for CMIP5, but for CMIP6, but CMIP5 as well. And so in most cases, we were able to get several ensemble members, the order of around 5 for certain submissions. For GIS, we had 10 submissions in addition to 2 different kind of physics versions of these. And so for 2.1, which is the low top version of GIS, we had submissions both that were coupled to the GOES ocean model, but also the HICOM isopycnal model. So there's a bit of at least ocean model diversity in some of these responses right here. And so in addition to the historical integrations, which could be directly validated and compared against observations or at least the reanalyses, we also made use of intermediary experiments. And so we had 1 intermediary submission from NCAR, 1 from GIS, and then 1 from the E3SM. And perhaps many of you have already seen some of the results from this, and we'll discuss this in the context of the quasi-biennial oscillation. And so then just to conclude, again, we had these subseasonal forecasts submitted from both the version 2 GEOS S2S product that Andrea Maulad has worked towards getting finalized, and they've had their paper submitted on this, as well as the GFS forecasts. And so with respect to validating the models, we used a range of observations and reanalyses. In particular, we used, for evaluating the MJO, we used the precipitation products. So we used TRIM for getting precipitation and the ERA5 for doing the analysis of the meteorological fields. For the QBO, we primarily leaned on MERA2, which previous studies have shown does a good representation at getting both period and the amplitude, albeit with some small discrepancies in terms of the actual peak of the QBO at higher altitudes. But overall, MERA2 does a very good job in representing the structure and the dynamics of the observed QBO. And then for the extratropical modes, a lot of the analysis was based on SST products, but also it was nice that Peter and John were also able to incorporate a lot of the 20th century reanalyses, so we could get somewhat better statistics in the rendering of these modes and comparisons with the quote-unquote observed values. So in terms of the metrics that we used, these also were tailored to the particular mode that we were considering. For the extratropical modes, we utilized the PCM-DI metrics package, performed comparisons of both the observed and modeled empirical orthogonal functions, and skill was illustrated primarily through use of tailored diagrams where we can see kind of a gross representation of the progression from CMIP 3 to CMIP 5 and then to CMIP 6. For the modes of tropical coupled variability, like the MJO and the ENSO, for ENSO, John used the climate variability diagnostics package, and for the MJO, the analysis was a bit more tailored to the measures that were used in Zhang et al. And we will go through what those were in the upcoming slides. And then for stratospheric variability, my analysis leaned very much on the metrics from Scherzinger that were applied recently in the stratospheric processes in the rolling climate QBO initiative, which was summarized here in Neil Bouchardt's paper, and then Yaga Richter has done some very, very nice analysis of what those runs are like in the historical type integrations, but also how those might respond to idealized climate change. So before I go into some of the details, I wanted to present first 3 bullets which summarize our main findings. And our first finding was that there are certain modes, namely the cases of the MJO and the QBO, where it does really appear that there is an unequivocal improvement in moving from CMIP 5 to CMIP 6. So that said, there are other modes, however, including many of the extratropical modes, for which the improvement in model performance from CMIP 5 to CMIP 6 is clear, but the story is a bit more nuanced. And so some of the improvements are more obvious when we condition on season, or when we look at some measures versus others, and or if we look across modeling groups or just within individual modeling groups. So these kind of our consensus or our feeling at the end of this was that robust improvements in the representation of extratropical modes still remains an important challenge for future model development. And so then finally, we found that it was very useful to incorporate intermediary simulations from the different modeling centers, as this was an attempt to identify if the improved model fidelity was actually a consistent response to similar changes across modeling centers. And so I'm going to begin with the main findings about the MJO. So the evaluation of the MJO centered primarily around an analysis of the signal strength of precipitation, shown in the top panels through these canonical Wheeler-Pilatus plots. And in addition to identifying the change in the amplitude of the signal strength at these wave numbers 1 through 5 with propagating timescales of 20 to 100 days, we were also interested in the coherence of the eastward propagation of those precipitation, in this case, lower zonal wind anomalies. And, you know, here we're just looking at the 850 millibar zonal winds, but we also looked at other measures like OLR. And this is a comparison for 2 different models, GFDL and CSM shown at the bottom. And for both of these cases, what we can see is that there's an improvement moving from the CMIP 5 version of the model to CMIP 6. And so you can see this both manifest in the signal strength of precipitation, but then also in this more coherent eastward propagation of these zonal wind anomalies. And so just to show you that this is not just exclusive to those 2 models, what we're plotting right here is the relative precipitation amplitude and pattern correlation for all of the models considered in this analysis. And so generally, what we see is a progression from the CMIP 5 versions of the models shown in the green to the CMIP 6 versions of those models shown in the blue. And the the value for the trim-based precipitation is shown right here in the gray in the gray star. And so what we can see is that generally, even though the degree of improvement depends very much on the modeling centers, there's a general tendency towards an improved representation shown here in the precipitation field. And so not just, we can look not just at correlations, but at somewhat higher order, more quote process-based measures, focusing on this east-west ratio, which is again that kind of measured degree of this propagation and the coherence of that propagation east. And what we can see again is a similar picture that in general, the CMIP-5 versions of the models shown in the green do exhibit an improvement when, or are improved when we move to CMIP-6. So of course, it depends on the modeling center. It's not always a clear progression, but in general, the blues are occupying this portion of the figure, and the greens are shown right here. And I would just like to note that this is not something manifest just in the precipitation, but is also a circulation improvement. And right here, the degree to which this is evident here could be a bit skewed by this outlier right here. But generally, again, we find CMIP-5 is located here and CMIP-6 in this corner. And so we found it instructive to incorporate an intermediary version of the GIST model E, and what's highlighted right here is an intermediary tag that had changes to both to the entrainment rates, but also to one of the parameters that controls re-evaporation above the cloud base. These changes having been documented in these papers by Daeun Kim and Tony Del Genio. And what we can see is that generally this intermediary version is sitting between the CMIP-5 and the CMIP-6 versions shown right here. And so, after discussion with Angel, even though of course the individual parameterizations differ, generally the class of changes that were made, which rendered the convective parameterization more sensitive to relative humidity in the environment, tended to result in an improvement in the simulation of the MJO in these models. So the second mode for which we found a clear performance was the quasi-biennial oscillation. And so generally what we found was a quite substantial leap in the performance of the QBO in this subset of CMIP-6 models that we were considering here. And in particular, this was quite nice to demonstrate, especially given that in the entire CMIP-5 archive, only 5 models had anything that was resembling anything so much as a QBO. So this is quite a substantial improvement. And so what you can see right here is shown in these pressure time plots of the equatorial zonal winds, both for MERA2 and then for all of the MoV models that we considered here. You can see that with the exception of 2 models, CSM2, which is again the low top version of that, and then the low top version of the GIST model E, for which we would not expect necessarily to get the resolved waves that would force the QBO. We can see that for the other models, we do see this this substantial improvement in the QBO. And so overall, we can attribute this to both increases in vertical resolution, especially in the UTLS upper troposphere, lower stratosphere region, but also to changes in the non-orographic gravity wave drag parameterizations, namely in the incorporation of not only convective sources, but also sources related to shear and frontogenesis. And so in particular, many of you perhaps have already seen these results that were nicely described in a paper that Yaga wrote last year. But what we can see is that in the original version, the default version of E3SM, the period of the QBO, which notably does exist, unlike in these lower vertical resolution version of the models, nonetheless, the period is too fast and has a characteristic timescale of about 16 months as compared to 28 months in MERA2 and in the observations. And what Yaga demonstrated and what we can see right here in this modified orographic gravity wave drag version of that model is that the period was substantially reduced and is much more in line with MERA2. And this was in response to changes in a quote efficiency factor, which controls the amount of parameterized convective momentum flux as it enters the lower stratosphere. So it's a lever on how much convection is contributing to the amount of momentum flux that's being deposited in the stratosphere. And I would just like to point out that with the GIS E2.2, which is the high top version of the lower of GIS model E, and so this is the low top version, we not only benefited from increased vertical resolution, but similar to some of the changes that Yaga contributed to E3SM, we also which convection, convectively driven non-orographic gravity wave drag enters the stratosphere. So this efficiency lever is the approach that we use, which is very similar to that was taken with E3SM. And so even though the changes in the momentum flux do seem to correlate well with QBO period, and thus provide a means to tune the QBO period, which we can see is generally well represented relative to MERA2. Again, you can see this improvement in the QBO period in the modified orographic gravity wave drag scheme. The QBO amplitude is something rather different, and in fact, we can see really no indication of an improvement when the amplitude of those momentum fluxes is changed. And this really presents an issue that has been known and has also been demonstrated for the QBOI models, and is physically translates to a kind of a lack of the QBO to descend substantially into the middle and the lower stratosphere. And so this amplitude underestimate does remain a challenge for models, and in particular will have implications for the degree to which QBO teleconnections to other modes like the North Atlantic Oscillation or the Madden-Julian Oscillation can be represented in climate models. So moving on to the extratropical coupled modes of tropospheric variability, here is more of a summary figure demonstrating an overall improvement or migration from the CMEP3 versions of the models to CMEP6, shown for ENSO, the PDO, as well as the southern and northern annular modes. Even though for the southern annular mode, it's really not quite so obvious that there's this improvement per se. But generally, there is a migration moving from left to right. Again, with the caveat that we're not looking at the entire CMEP6 archive and focusing rather on the 6 climate models analyzed in the study. And so, however, if we take a bit more of a nuanced view, looking at each individual mode conditioned on season, the story is a little bit different and is a little bit more complicated compared to the improvements that we were seeing with the MJ and the QBO. And in particular, here's a Taylor diagram showing that for during December, January, February, the southern annular mode does exhibit what could be seen as a improvement moving from CMEP3 versions of models shown in the pink to the CMEP6 versions shown in blue. However, if you look at the SAM during summer, winter, so during June, July, August, you can see that the story is actually quite a bit more complicated than that. And if anything, there may be some indication that the CMEP6 versions are actually exhibiting somewhat degraded performance, again, by comparing the red to the blue. We can also see that the changes in the performance of the northern annular mode, it depends on whether or not you're looking at across models, but also within individual modeling groups. And so, for example, if we just looked at the CMEP evolution in the GFDL group, we can see what seems to be an overall improvement. It's definitely an improvement moving from CMEP3 to CMEP6. And then we see actually the opposite behavior in the GIS model E submissions with a somewhat degraded performance again in the CMEP6 versions. At the same time, again, this is quite model and group specific. If we look at the North Atlantic Oscillation, again, even though we may be seeing somewhat of an improvement in CMIP6 across all the models, if we look at individual modeling groups, here we're looking at different versions of CSM, we can see that perhaps there is somewhat of a degraded performance in the North Atlantic Oscillation, again, for this season. So the overall story is that it depends very much on the modeling group that you're looking at, and the season and the mode. That said, perhaps one clear indication of improved extratropical mode representation is in the Pacific Decadal Oscillation. And this is a figure that John put together where he's looking at the principal component phase space of PC1 and PC2, which explain most of the variability of these sea level pressure anomalies. And what we can see is that for the colors, which are highlighting the CMIP5 to CMIP6 progression moving from here to here for the case of the GIST model, and here for GFDL, and here for CSM, we can see generally that in this PC1, PC2 phase space that the models are migrating in the right direction. That said, they're underestimating the amplitude quite significantly relative to the observations, but there is a general tendency towards an improvement in these model versions. And so in terms of the evaluation of ENSO, of course, one important thing we'd like to know about ENSO is teleconnections to higher latitudes. And so this figure right here shows sea level pressure boreal winter composites over El Nino events. And this is based on the 20th century reanalysis. And if we compare that to the pattern of the mean CMEP bias, so now we're not distinguishing between 3 and 6, but in general, we're looking at all the models, we can see that the amplitude of these teleconnections to higher latitudes is underestimated. And that's evident in the sense that the mean bias is opposite in phase to the actual climatology of this the sea level composited events over ENSO. And so generally there's an underestimate, and we see that manifest over the Pacific and the Atlantic, and then also over southern high latitudes. And so it's interesting to look at ENSO from kind of an impacts perspective, and to do so, one can look at higher, more of a spectral decomposition of ENSO into different frequencies. And so if we do so and we look at how the performance of ENSO is compared to, these are observational constraints, again, decomposed into different frequency bands, we can see that actually there's been a degradation in the performance of ENSO among certain models. And so we can see, for example, in the GIST submissions, that the amplitude of ENSO has actually increased relative to CMIP5, where the amplitude of ENSO was actually smaller than observed. Same thing can be seen in CSM. You know, this is just an important reminder that when it comes to really evaluating the kind of higher order impacts, we should be looking not just at kind of basic mean climatologies, but also at how ENSO is being simulated in these different frequency bands. And so this is something that merits more looking at, and complicates our rendering of these general improvements that we've been seeing across the CMIP versions. And so again, we're going to make use of an intermediary model experiment, and that's what's shown in these plots right here, where we're looking at the regression between sea level pressure and 3.4 SST index, shown here for the reanalysis. And what we're looking at right here is the difference between two simulations of CSM2, and the CSM2 gamma version. John contributed this intermediary experiment where he changed a variable that controlled the width of the vertical velocity PDF, which is a factor that goes into the Club-Child convection scheme. And what he's showing right now, I'm looking at these differences in the case where gamma has been perturbed from its default value, is that we see this perhaps unexpected impact on teleconnections at higher, nice and perhaps unexpected impact on higher latitudes. So again, even changes in tropical convection can substantially change teleconnections to high latitudes. So currently we're analyzing this to see whether or not this is through modification of the actual Rossby wave teleconnections at high latitudes, but this was a quite nice demonstration that impacts in convection really here in the tropics can affect the amplitude of these teleconnections at high latitudes. And so even though, again, our focus primarily was on looking at climatic timescales, we did incorporate 2 of the subseasonal products. And in particular, for the case of stratospheric winds, we wanted to ask, were the improvements in vertical resolution in the UTLS region, did those not only produce improved representation of the quasi-biennial oscillation, but could we see improved forecast skill on shorter subseasonal timescales? And so what I'm plotting right here is the root mean square error in the subseasonal forecast for the GEOS subseasonal product and for the GFS. And what we can see is that in the troposphere and the UTLS region, maybe the difference is not quite so evident. And if anything, the NOAA forecasts seem to be exhibiting somewhat improved performance. But as we go up in the stratosphere, where the increases in vertical resolution evident in GEOS appear to be a bit more evident, we can see that there's less error, and so this is some indication that the changes that are being made that have resulted in improvements on longer time scales might also be contributing to improvements on shorter subseasonal time scales. And so with that, I would like to conclude. I was told to keep this talk to about 30 minutes. So this is a relatively brief discussion of what we found. And again, the origins of this project was the U.S. Climate Modeling Summit, which gathered together people from 6 U.S. climate modeling groups. And we performed this analysis, submitted it before the Working Group 1 deadline. And the result of that was this paper right here, which is currently under review. And so just to summarize the main key points, I think what we've seen is that for some modes, there has been a clear improvement moving from CMIP 3 and 5 to CMIP 6, and these include the MJO and the QBO. The story, however, for other modes like the NAM, other extratropical modes, as well as ENSO, is a bit more nuanced and depends on the measure one is considering, the season, and whether or not one is looking within or across modeling groups. What we've seen is that, again, certain aspects of variability, like the ENSO spectra, but also aspects of QBO, namely the QBO amplitude, remain key challenges for future model development. And in particular, things like the QBO amplitude will affect QBO teleconnections to the MAO and the MJO. And so really pinning down what is causing the underestimate in the QBO amplitude is something that will remain challenging. And so finally, we found it quite illustrative to look at intermediary model versions, and as compared to other intercomparisons which utilize publicly available CMIP data, we found that these versions were key in helping us to identify exactly which developments did contribute to these improvements. And so, one of the lessons here is that even though, there exist several of these model tags, and we as modelers may feel that we don't have a lot of time to analyze it, we found that these have actually been quite useful. So there's a potential that any model tags you may be having around in your archives may actually be important and show and be very useful for summary papers along these lines. So with that, I'd like to conclude and thank you very much for listening, and I'm not sure how the questions are being taken, but I'll pass this off to Luke.